Okay, let's get back to work here. Part 2. So I looked at that and you hopefully have had fun with that one. So then we get this wonderful character called Max Planck, and he's actually really quite important. Planck has a huge career as a scientist, and there's many Max Planck institutes throughout Germany named in his honour. Where do we start? Why is the H so important in uncertainty? H is equal to 6.63 times 10 to the minus 34 joules per second, and it's what's called the Planck constant. What this says is that energy is not continuous, but comes in these finite bursts of Planck constants. So every little burst of energy is 6.63 times 10 to the minus 34 joules. And they're coming regularly, otherwise we'd have big black spots between the light from the sun. So obviously they're pretty close together, and our eyes aren't tuned to tell them apart, but you can measure them apparently. Einstein used this idea to explain certain properties of light. He said that light was in fact a particle with energy E equals h, Planck's constant, times velocity. So the energy was Planck's constant times the speed of that light. So if light's 300 kilometers per hour, what am I saying? 300 kilometers per minute, per second? No, hang on. Whatever it is, you know what I mean. It's moving. It's got a lot of energy stored in it. So after that, the idea that energy isn't continuous was taken as a fact of nature. There was now a reason why electrons were only found in certain energy levels around the nucleus of an atom. So depending on how much energy it contains, determines how far it can stray from its nucleus, which leads, of course, to a much different model of the atom that you're used to. Also, by combining Planck's constant with the constant of gravity and the constant speed of light, it's possible to create a quantum of length, which is 10 to the minus 35 meter, and a quantum of time, 10 to the minus 43 second. And of course, these are Planck's length and Planck's time. Although it may seem like the idea that energy is quantized, it is a minor part of quantum physics. That's a horrible sentence. Although it may seem like the idea that energy is quantized is a minor part of quantum physics when compared with ghost electrons and the uncertainty principle, it really is a fundamental statement about nature that causes everything else we've talked about to be discovered. That's a horrible sentence, isn't it? And it is always true. In the strange world of the atom, anything that can be taken for granted is a major step towards an atomic world view. And we try, I suppose, in science, work towards that idea. So who is this Max Planck? Why did he get so much stuff named after him? He must have been pretty famous. He must have done some good stuff. So onto the log for you guys. We've talked about Schrodinger's cat, we've mentioned on the way past. So quantum physics leaves us with a rather large open question, which you're going to have a go at answering soon, of what is reality? And the Copenhagen interpretation attempts to solve the problem by saying that reality is what is measured. So if you can't measure it, it's not real. However, the measuring device itself is then not real until it is measured. The problem, which is known as the measurement problem, is when does the cycle stop? So, imagine a box in which is a radioactive source, a Geiger counter, or anything else that might record the presence of radioactive particles, a bottle of cyanide, and a cat. The detector is turned on for just long enough that there is a 50-50 chance that the radioactive material will decay. If the material does decay, the Geiger counter detects the particle and crushes the bottle of cyanide, killing the cat. If the material does not decay, the cat lives. To us outside the box, the time of detection is when the box is opened. At that point, the wave function collapses, we're observing, and the cat either dies or lives. However, until the box is open, and this is where Schrodinger likes playing with their heads, the cat is both dead and alive. So, on one hand, the cat itself could be considered the detector. Its presence is enough to collapse the wave function, but in that case, would the presence of a rat be enough? Or an amoeba? Where's the line drawn? On the other hand, what if you replace the cat with a human? Called Wigner's friend, after Eugene Wigner. It's the scientist who developed many derivations of the Schrodinger's cat experiment. The human is certainly not able to collapse the wave function, yet to us, the human is certainly able to collapse the wave function, yet to us outside the box, the measurement is not taken until the box is open. If we try to develop some sort of quantum relativity where each individual has his own view of the world, then what is to prevent the world from being out of sync between observers? And of course, if you've got a human inside a box who can report back to you about things, does that again change the point of observation and undo Schrodinger's cat? Thought. If we have time, we might have a go at this. Can you design a thought experiment that recreates Schrodinger's experiment without killing anything? Remember, it's a thought experiment. You don't actually have to run it. But you can, of course, be quite inventive in a thought experiment. You don't need to have the equipment. We're going to have to spend a class actually doing this task, because this is the thing that really makes this all worthwhile. Having considered all these things that are considered in quantum physics, can you answer the question, what is reality? Remembering to Bohr's idea from the Copenhagen interpretation, if you can't measure it, it ain't real. Limits us a bit, doesn't it? Then we have a thing called the infinity problem. So this is essentially a mathematical part of quantum physics called quantum electrodynamics, QED. This branch of quantum physics explains the electromagnetic interaction in quantum terms. So the problem is when you add the interaction particles and try to solve Schrodinger's wave equation, you get an electron with infinite mass, infinite energy, and infinite charge. And there's no way in usual valid mathematics to remove the infinities. So theorists simply divide infinity by infinity and basically plug in whatever numbers they like. So they've fudged the maths. The other results of QED are so powerful that most physicists ignore the infinities and use the theory anyway. So this idea of QED is actually really quite a powerful part of modern physics, and your mobile phone essentially works because of it. Paul Dirac, who was quite a famous mathematician and physicist prior to Schrödinger actually, said, sensible mathematics involves neglecting a quantity when it turns out to be too small, not neglecting it just because it is infinitely great and you do not want it. So he wasn't a big fan of quantum physics. Another interpretation presented by Hugh Everett in 1957 is many worlds or branching universe interpretation, and you often find this sort of stuff in string theory, another variety. In this theory, whenever a measurement takes place, the entire universe divides as many times as there are possible outcomes of the measurement. All universes are identical except for the outcome of that measurement. Unlike the science fiction view of parallel universes, it is not possible for any of these worlds to actually interact. So not entangled in the way we saw in entanglement theory, because entanglement theory is looking at really particles within a universe. This is universes parallel with each other that don't interact. So you can't use little wormholes to move from one to the next. While this creates an unthinkable number of different worlds, it does solve the problem of Schrodinger's cat. Instead of one cat, we can have two, one dead and the other alive, simply living in different universes. But that doesn't solve the measurement problem. If the universe split every time there was more than one possibility, then we wouldn't see interference patterns. So, when does it split? And at this point in time, no one has an answer to that question. So, lots of wonderful questions to be thinking about. Lots of interesting stuff to play with. We're going to have lots of fun experimenting with this stuff. And I'm hoping that you'll have a bit of fun thinking about, so, what is reality? Looking forward to catching up next term when we get to do all this stuff together.